we'll get to localization. So this is sort of a current plan of an outline, crude outline of the talk. First, I'm going to just sort of review things just to make sure we're all on the same page. And then I'm going to talk about thermalization, and then I'm going to talk about many-body localization. Let me just, at the beginning, thank my longtime collaborators in this subject. Vadim Oganessian, almost 10 years ago, got me interested in this subject convinced me that it's an interesting subject to look at quantum dynamics at very high temperatures. And at that time we didn't have disorder, and we were doing thermalization, but we didn't even know to call it that. And that was with my student Subrata Mukherjee. And then in 2005 there was this work, I think it was published in 6, I'm not sure, of Bosco, Elena, Altschuler talking about many-body localization. And again, Vadim convinced me that this is a good, important thing to look into from different perspectives than Russian perturbation theory. Right, so I really thank Vadim, since he sort of set the topics for a large fraction of my research in the past decade. And then Arjit was my graduate student who worked on many-body localization, wrote a thesis. An interesting thing about this is we got into this subject in 05 and 06, that kind of vicinity. And for a long time it was very lonely. Almost nobody was working on the subject. And every morning I'd come in and look in the archive and say, yeah, still nobody's working on the subject. And that went on for long enough for Arjit to do a very nice PhD thesis and graduate. But some of you who have been following the field, just in the past, in 2013, just the past few months, all of a sudden, a whole bunch of theorists have jumped into this field of many-body localization, which I was expecting to happen much earlier. Okay, so there's a general topic here, which is thinking about quantum many-body systems strongly interacting, strongly entangled at high energies, and taking seriously the quantum dynamics and just trying to understand what happens from the point of view of really thinking about unitary time evolution of an isolated quantum system in that regime. That's the general theme here. And so this is, unlike the usual approach to a lot of condensed matter physics, where you talk about the ground state and then you look at a few excitations on the ground state. That's not at all the idea of what we're doing here. We're not anywhere near the ground state. We're not in a regime where a simple description in terms of a few quasi-particles is appropriate. We're talking about very highly excited systems. That represent thermodynamic, if they went to equilibrium, which they sometimes do and sometimes don't, that would represent some non-zero temperature, some non-zero energy density above the ground state, and often, for simplicity, we just take infinite temperature. So highly excited. Okay, so we start with. Now I'm going to start with this. And when you study thermodynamics and statistical mechanics, you often are discussing this situation here of system isolated from its environment. And that's what we're going to be talking about here. Okay, if the system is coupled to the environment, let's just put the environment inside the box. Okay? And then put a bigger box. Right? And so it's not that I'm not talking about systems coupled to environments. This could be a system coupled to environment in here as well. But then we put a box around it. And this system has a Hamiltonian and is undergoing unitary time evolution. Or I guess we could also have this Hamiltonian So either that Hamiltonian is time independent, or there's also the case, which you've heard about in these lectures, or in this course, this school, whatever, where this Hamiltonian is strictly periodic in time, and you have a Floquet system, like a kicked system. So either H is time independent, or H of t equals H of t plus n10. So that's the Hamiltonian of the system. Now, of course, this is something you're used to from courses, right? This is what you always do when you talk about thermodynamics and physical mechanics. And so it's familiar. It's sensible to do that. And let me just give some examples of other reasons why we should be interested in such an idealized system. Okay, so yeah, let me just, I want to mention an example. So an early example, bringing up the possibility of these two different behaviors is from Anderson's original paper about localization. So, for example, what Anderson, in his original paper about localization, it looked like this. He was talking about the spins. Did you know Anderson's paper, original paper about localization, was not about particles hopping in random potentials? It was about many-body localization. So this was about many-body localization. And he only did single-particle localization as an approximation to the problem he was working on. You should look back at the paper. So what he did, people were looking at the dynamics of spins, localized spins that were in lightly doped semiconductors. The spins were immobile. They were on dopants. And they were looking at the dynamics of those spins. And Anderson asked the question, what if I just consider the spin-spin interaction and ignore the spin-phonon interaction? And so the idea here would be you have the spins, they're interacting with each other. That's my strongly interacting quantum system. And the environment is the phonons, and we've decoupled it and made that approximation. So this is an example, and that's sort of the beginning of all this. Anderson, 1958. But more recently, things like this, of course this is a many-body system, you could be talking about some sort of trapped, it doesn't have to be cold, trapped atoms, or ions, or molecules. And there's enormous effort now in the AMO community, experimental community, to study these systems and to make systems which are a good approximation to this. So these people experimentally approximate this reasonably well and do all sorts of nice experiments. And then another motivation for all this is sort of an idealization of a possible type of quantum information processing system. Or certainly you'd like to have a bunch of interacting quantum degrees of freedom, and you'd like to isolate it from the environment. So certainly thinking about this physics brings one also to thinking about what really happens in interacting many-body systems undergoing the unitary time evolution of quantum mechanics. Okay, so those are sort of three motivations in addition to the familiarity from courses. We always do this. Okay, now since Anderson started with spins, and spins are, when you're doing quantum systems, spins are particularly spin and halves, two-level systems. It's about the simplest situation. to think about, and so that's what I'm going to discuss things in terms of most of the time, except when we want to add other degrees of freedom. So an example would be in two-level systems, whose operators we can write as the Pauli operators, sigma I, and these could be spins, or they could be qubits of some sort, or they could be orbitals for fermions, which are occupied or empty. Those are the two states, or for hardcore bosons, so orbitals that can have occupancy 0 or 1. That's a nice two-state system. So my two-level systems could be physically any of these or any other two-state system you might make. Okay. And then we're going to have a Hamiltonian, and let's just talk about a Hamiltonian with single spin terms and two spin terms. So the Hamiltonian in general is going to look like this, sum over I. And I will be thinking about systems that are disordered, have static disorder. So each spin can have its own field. And then the spin-spin interactions. So we just write it rather generally like this. Okay, so this is single spin terms. What's the Hamiltonian of a single spin not interacting with the others? And this is the most general Hamiltonian of a two-level system. It's just a Pauli matrix in a field. These are, now, an important thing I want to do is restrict myself to short-range interactions. Okay, my spins are immobile on some places in space, perhaps on a lattice, or perhaps just randomly placed, like the spins that were doped into the superconductors they were talking about here. And let's say the interactions are only over short distances. And in general, we could think of any interaction, right? So this has 3 components and this has 3 components, so there's possible 9. This is a little 3x3 matrix of all possible interactions. But if you want to be a little more, even more specific, we could talk about the transverse field Ising model, which you've seen a number of times in this course. So I can write this as sum over I, hi, x, let's follow. A transverse field, allow it to be random. So here I'm putting all the fields along the x direction in the space of those Pauli matrices, and then we could have an Ising interaction, Ij, Jij, sigma z, sigma zj. So that's the transverse field Ising model. So we could be talking about this, but it could be other spin models. Gil talked about various other spin models. I think the other spin models have been on the board during this course. Okay, if these are particles, so this is short-range interactions, and sigma plus I, sigma minus j is a hopping, right? And so if my sigmas represent particles that are occupied and empty, then the raising and lowering operators of the spins are the creation and annihilation operators of the particles. And so if I had a term in here which was sigma plus, sigma minus, that would be a hopping term, right? And so this is not only interactions but also hopping, if we're talking about particles.
Are you not including the identity matrix matrix, like in a set of 4 2x2 matrices? So the three,
Yeah, okay, so if the identity couples to this spin, that's over here. Right? Okay, so if we take two spins, there's 4 operators, including the identity, for each spin, so there's a total of 16 terms. I've got 9 of them here, 6 of them here, and then there's the identity. The identity on both spins, the product of the identity on both spins. And you know, of course we can add a constant to the Hamiltonian, but that's, I'll generally leave those out because they have no dynamical consequences. Yeah, but I'm going to come back to that, your point again.
Is the physics going to depend on which choices you make, like whether it's Heisenberg or Ising?
Okay, so the physics I'm going to be talking, that was my next point I'm going to make, right? Okay, so this could be fermions, bosons, they could have different symmetries, it could be 1D, it could be 2D, it could be 3D. The physics I want to emphasize in my lectures is the physics that doesn't depend on those details. Okay. Now if we're in 1D and we choose some Hamiltonians, it might be integrable. And I'll mention that a little bit in passing, but ideally I'm talking about non-integrable, strongly interacting systems, and I'm going to focus on the aspects of their physics that's general, that doesn't depend on symmetries, although occasionally things will depend on symmetries, but if I don't mention this is specific for such and such, I'm trying to be general, but please interrupt me when it's not clear.
But even beyond symmetry, like including hopping term or not including hopping term? Sigma plus, sigma minus.
Well, we want...
That's in the Ising. In the Ising model, you get sigma z, but not.
Yeah, but I have a transverse field.
Oh, okay, so that's dynamics, but it's not.
So if this was a particle Hamiltonian, sigma x, this would be a particle and this would be opposite, and this does contain hopping terms. Right? Sometimes people write the transverse field Ising model with z here and x here and x here. And of course x contains the raising and lowering operator. So I really have the hopping terms here. When you at least hopping terms, if we think of sigma x as the variable which tells you whether you have a particle or not.
Okay.
Right, if you think of sigma z as whether you have a particle or not, then I don't have conserved particle number, even modulo 2. And this just annihilates and removes particles. But this shouldn't be talked about as a particle. Except in 1D, when it's integrable, you map it onto free fermions, and then it's okay. But you know, this is I want to do this, say, in 2 dimensions or in 1 dimension with further than nearest neighbor interactions, where it's not equivalent to a non-interacting fermion property. Okay. Okay, so when we talk about this system, we could talk about pure states. Psi, states in the Hilbert space, wave functions. And I just want to make a comment, so I'm going to preach a little bit about quantum mechanics. I hope you won't mind. So pure states are a nice idealization and tool. And this is not emphasized very much in teaching and textbooks about quantum mechanics. That real quantum systems do not have wave functions. They're not in pure states. Pure states are, but the pure states are a very useful tool in doing calculations. But they're, in general, only approximation to real mixed states, which we can denote by rho. Okay. So rho, okay, again, I apologize for those of you who don't want to hear preaching about quantum mechanics. I was invited to speak, so I will. So rho, this is commonly called the density matrix, right? And it usually is presented as a technical tool that you use sometimes when you need it, but it's not very central to quantum mechanics, right? Whereas I want to insist that this is the central object in quantum mechanics, and we shouldn't call it the density matrix because that totally obscures its importance and its meaning. And so I want to rename this the probability operator. Okay. Which is also known as the density matrix. And this two-word phrase really emphasizes both what's important about this and also what's different between quantum mechanics and classical physics. Right? Quantum mechanics is a probabilistic theory, and rho is the probability. And it's not a scalar probability like in usual probability theory, it's an operator. Right? And what makes, these are the two essential things which makes quantum mechanics interesting and different. It's a probabilistic theory, and the probability is an operator that doesn't commute with this. And quantum systems are always in some mixed state, which is given by a probability operator. With great care, you might be able to approximate some sort of pure state. But any real experiment, you've always got some imperfections and some mixture in your state. And often the mixture is because this system, right, I said it's isolated from its environment, which is a statement about the Hamiltonian, but it might be entangled with its environment. The system could be entangled with the environment, but not interacting with the environment. And typically it is, because you had to prepare this state somehow in the lab. And in that preparation, you almost inevitably made some entanglement with the environment, unless you've really put the system in its ground state. Right? If you really get it in its ground state, then you have a pure state. In reality, that's only an approximation.
Can we write an expression for probability operator? Is it?
Okay, well let me just say this. For a pure state, rho is equal to the projection onto that pure state. And more generally, for any operator, the expectation value, this is any operator, the expectation value of the operator is trace rho n. So rho is the operator that for every observable satisfies this equation. That the expectation value of that observable in that system is equal to the trace of rho times A.
So it's not e to the minus beta h.
At equilibrium, it's e to the minus beta h. But in general, it isn't. Right? That's again, that's an idealization. In fact, it's never e to the minus beta h, as far as I know. No, I should be careful. If you take a small subsystem of a large system which went to equilibrium, maybe I should say it's never e to the minus beta h. Because in order for it to be accurately e to the minus beta h, you have to have it coupled to its environment. But then h includes the environment, right? And so what do you mean by e to the minus beta h? Right?
You said you can put the environment in your box, so it's the box itself.
Right. but then what's the state of this system? But we'll get to this. We'll revisit these questions. Okay, so what properties does the probability operator have? It's a probability. It's normalized to 1, so trace of rho is equal to 1. The spectrum of it, spectrum of rho is in 0 to 1. Like I said, trace 1, non-negative. It's Hermitian. Rho dagger equals rho. And for pure states, it's just this guy. So if we talk about probability operators, we're including pure states. Pure states are included as a special case. Okay, and now our time evolution. Is rho of t equals e to the I h t minus h equals 1 times rho of 0. Plus. Or for Floquet, rho of t plus n tau equals u to the n rho of t u dagger to the n, where u is the unitary evolution operator which gets you through one cycle of the period of the Floquet system. So u advances you forward on the tau. Or backwards. Whoops, no, that's an n. Actually, let me put this as a, do this a little differently. So that's supposed to be that n. And I'm just going to write this as u to the minus n, which means the inverse to the nth power. Right. So these bring you both forward in time and backward. Right. And then what's this? Time reversal. Go forward in time or backward.
This is a Schrodinger picture.
Yes, that's the next point. This is, yeah, I should have said that first. I am going to work in the Schrodinger picture. And actually, let me just write down the time evolution. So I h bar d rho dt equals h commutator rho. That gives the time evolution.
There's a funny operator that involves in Schrodinger picture.
Excuse me?
Rho is a funny operator that involves in Schrodinger picture because it's really a wave function. Or it's really related more.
Rho is the state of the system. Schrodinger picture,
No, I know. So,
the observable operators are time independent in the Schrodinger picture, and the state evolves.
right. I'm just saying it's a funny thing to call it the operator because.
Call what?
There's states and they're operators. Operators evolve with either a plus IHT.
Well, okay. There's the physical observables, which are operators,
Right.
and there's the state of the system, which is an operator. And when you do the Schrodinger picture, you choose to put time dependence on the state of the system and not on the physical observable operators. Right? And in the Heisenberg picture, you do it the other way around.
It's just your new definition or your new terminology for density matrix.
Well, it's not an observable operator. You know, it's the state of the system.
Right.
So it's playing the role of the wave function in the usual Schrodinger. This is the Schrodinger equation, right?
Yeah.
I think von Neumann first wrote that down. And this gives the time evolution of the probability of the system.
What's all?
If it's a Floquet system, so this is the special case of the Floquet system where instead of a time-independent Hamiltonian, we have a time-periodic Hamiltonian, like a kicked rotor type thing like Delon was talking about. So if you have my discussion generalizes to systems that aren't strictly time-independent Hamiltonians, but Hamiltonians which are periodic functions of time. And then the time evolution through an integer number of those periods is reasonably simple like this. And this unitary operator is the operator which gives you the evolution through one period. Whose logarithm is kind of like a Hamiltonian, although not exactly. Actually, just a little comment. I don't know if anybody noticed, but today in the New York Times, on the op-ed page, there's a little essay about quantum mechanics, about the uncertainty principle, written by a philosopher. They have this series in the New York Times with little philosophy essays on the op-ed page. The guy actually did a pretty good job. He wrote it. Some philosopher. But he obviously really knows a lot about quantum mechanics. I recommend looking at it. It's very quick, easy to read, and it's, I don't know. Seems like it might be accessible to people who don't know a lot of quantum mechanics. It seemed like a good job writing this kind of stuff. It's just funny, I saw it this morning. Okay, yeah, right. So about the pictures. Okay, so in Heisenberg, rho is independent of time, and physical observables evolve and become, in the general types of systems I'm talking about, very complicated. Right? So I'm talking about systems where the time evolution, this is very complicated. Right? Okay? And the Heisenberg picture is nice if you're talking about states that are simple. Then you have an advantage. You get to stay with a simple state. But I'm going to be talking about complicated, highly entangled states. So the one advantage of the Heisenberg picture, I don't really have. Whereas in the Schrödinger picture, what happens is rho depends on t, and the physical observables are time independent. And I will be interested in simple physical observables. That's typically the only ones you can measure in the lab. And so at least in the Schrödinger picture, if you're talking about simple physical observables, they stay simple. And so that's why I argue that for the type of physics I'm talking about today, the Schrödinger picture is really very much preferable. Because we're interested in complicated states, complicated time evolutions. But we want to think about things you can measure on those systems, which are simple physical observables. And so the Schrödinger picture keeps that simplicity where it is, put where it is. Whereas up here, you would take your simple physical observer that become very complicated, and at the same time your state is very complicated. And so I guess that's an argument for why Schrödinger is preferred for the type of physics we're talking about today. Okay. Any other questions? Okay, so say we have, like I say there, n two-state systems in our system. So our full system consists of n two-state systems. Then we have 2 to the n dimensional set of pure states. Dimensional, 2 to the n linearly independent pure states. And And you can choose a basis. And a common basis to use is the eigenstates of sigma z. So for example, one of these states might be up, spin 1, cross, down, spin 2, cross, blah, 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 cross, let's say, up, spin n. So if I do this with all possible binary strings of up and down, that's the 2 to the n states. They're orthonormal. Right, so this is now a ket for a single spin. The many-body state of the full system is a product of these. So that's my set of pure states. Now for mixed states, okay, rho in this basis, for example, can be written as a 2 to the n by 2 to the n Hermitian matrix. So they're in fact 4 to the n minus 1. 1 for the normalization. Linearly independent mixed states. Actually, I shouldn't say that. That's a detail. 4 to the n linearly independent mixed states. And you can count them various ways, right? You could write out this matrix, and you could say, oh, the elements on the diagonal have to be real, and the ones off the diagonal are complex, so they have 2 coefficients, the real and the imaginary part, and you count that all up, you get 4 to the n. But a nice basis in quotes, for the mixed states is using the Pauli operators. So they're 4 to the n linearly independent mixed states, and they're also 4 to the n linearly independent observables. Right? Because any Hermitian operator could be the state of any Hermitian operator satisfying these constraints could be the state of the system. And none of these constraints are equalities, right? It's Hermitian, but these are just inequalities. Sorry, this is an equality. But, you still have 4 to the n of them. So the set of all Hermitian operators is basically the set of all possible mixed states, but it's also the set of all physical observables. So therefore, 4 to the n linear independent mixed states, and therefore 4 to the n linear independent physical observables, 4 to the n linearly independent Hermitian matrices for this system. And that comes from 4 per spin. So each spin has an identity matrix. So say this is the identity matrix on spin I. And you might think of that as the 0 component of the Pauli matrix, give it a 4th component. And then there's sigma xi, sigma yi, sigma zi, 3 Pauli matrices. So these are the 4 linearly independent Hermitian operators you can have on a 2-state system. And then these 4 to the n, we can just list them all, e.g. sigma n1 on site 1 cross sigma n2 on site 2 cross blah 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 cross sigma n sub n on site n. And these n's, n sub I equals 0, 1, 2, 0, x, y, or z. You can have an identity matrix, an x, y, or z. So those are the 4 to the n operators. So if you have a many-body system and you want to ask, let me list all physical observables, I've just done that for you. Now usually when people write out these operators, okay, so these are outer products. This is an operator on just this spin. You need an outer product of them to get operators on the full many-body system. Usually when people write out these operators, like here, right here I wrote an operator, right? This operator here really is identity on spin 1 cross identity on spin 2 cross blah 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 cross sigma x on spin I cross all identities up to identity on n. And usually when we write out many-body operators, we don't write the identities and we don't write the crosses. We just write the non-identity ones like this or like this. Right? So this operator here or this operator here, these are many-body operators in this set here, but they're ones where almost all of the terms in this product are identities. And those are the operators that are physically accessible in an experiment. Right? If you want to measure something, you might be measure the spin, you might be able to measure the spin-spin correlation with neutrons, but to measure a 15-spin operator, extremely difficult. In fact, probably never been done with 15. I'm not sure what the highest. People are constantly pushing that kind of number, but 3, 4, 5 spin operators, I think that's the limit these days. So, amongst these operators, we have operators that people in quantum information call local, and that doesn't mean local in real space. So over here I didn't say local interactions, I said short-range interactions. So I'm going to use short range, I'm going to try to use short range when I'm talking about real space, and this local is something else. Local operators so in fact they would say k-local operators have n minus k identities and k non-identities. So this is a one local operator, this is a two local operator. And also, if you add together k-local operators, it's still k-local, right? So even if I take this sum, the whole thing, where I'm summing over them all, this is still a one local operator. The only way you increase the k is by multiplying the operators, not by adding them. Okay, so there's k-local operators. So there's the local operators. And now when we talk about a large system, when n is large, and let's say the operators are only local if this number k is of order 1, of these 4 to the n operators, almost all of them are not local, they're global operators. So the typical operator is what you might call global or non-local. And it'll have k of order n. In fact, typically 3/4 of n. Right? The vast majority of the operators have 1/4 of the things in these products are identities, 1/4 are x's, 1/4 are y's, and 1/4 are z's. Right? And these are operators that are very hard to measure, essentially impossible to measure. But in fact, physical systems under unitary time evolution, the probability operator becomes of this type. And that's part of what thermalization is, and that's what dissipation is. When people say dissipation, what they really mean is it just got too complicated to measure. It's not that it went anywhere, it just got too complicated to measure. And so we just stop trying to keep track of it and say it's gone. When you say decoherence, that's what it means. Okay.
Is there significance of this counting that, when you count each of the density matrix states, you have you have the same number of observables states?
Well, they're Hermitian operators. Essentially, every Hermitian operator. Okay, so there's a physical observable could be any Hermitian operator. Now you have this restriction for the pure states. Of course, you can just normalize it to this. So it has trace 1. So that doesn't remove the number of linearly independent ones. But you have to put this restriction on it. The spectrum is between 0 and 1. So you have to restrict it to, basically what you have to do is you have to, if you have a general Hermitian operator and you want to convert it into a viable probability operator, first of all, what you got to do is you got to find its spectrum, find the most negative eigenvalue, add the identity times that, so now the spectrum is all positive. Okay, find the highest operator, the highest eigenvalue, well, no, and then take its trace, and then normalize it to 1, so its trace is 1. So you can take any Hermitian operator, and just by adding the identity, you can make a probability operator, which is a viable state of a quantum system, out of it. Right? And so that's why the count is the same. It's really the same set up to the identity. Okay? Okay, so now we're ready to start. Good. Moving right along. Am I going too fast?
No.
Please ask questions. I'm ready to. So that was section. That was, well, I'm going to start talking about thermalization. So in some sense, this sort of terminology and dynamics. Okay. So, what is thermalization? So we have this story they tell when you do quantum mechanics, not quantum mechanics, you do equilibrium statistical mechanics. You take your system and you isolate it from the environment, and you wait long enough, and it goes to equilibrium. It's ergodic. What does that mean in a many-body quantum system undergoing unitary time evolution? So that's my next topic, and that's what thermalization is about. Thermalization means going to thermal equilibrium. Okay. This is an assumption, very hard to prove. There are some models where you can show that it happens, but it's basically an assumption that you use in statistical mechanics and mathematical physicists. Very simple models, they can prove that things actually are ergodic. And the question is, what do they really mean by ergodic? And so they have all these different definitions of ergodic. But general systems, it's like way out of reach for the general statement.
You're talking about a closed quantum mechanical system? Anybody?
Yeah, closed system, just like I had at the beginning. Here it is. System. It has its Hamiltonian. It's isolated from the environment. Okay, so the standard story that you assume when you do equilibrium statistical mechanics, that if I start with this system at a certain energy, any initial condition at that energy, and I wait long enough, it'll go to equilibrium. And it'll be in the microcanonical ensemble for that energy. And that's what I'm talking about. So, but let's say it's a closed quantum mechanical system undergoing strict unitary time evolution. So what does that standard statement really mean for a closed quantum mechanical system undergoing unitary time evolution? That's my subject right now. Okay. Yeah,
How do you define equilibrium without heat?
that's my next topic, is how do we define equilibrium? Yes, it's a
So
non-trivial question.
Without a heat bath. So
Exactly. That's what this talk is about, is answering exactly that question. And I can't do it in, that's what I'm going to do right now, is answer that question. So thank you for asking it. But the answer takes a while. Okay. So basically, closed system goes to thermal equilibrium, or T goes to infinity. What does this mean? Right? And it's not clear what it means. And in fact, some of its meanings are false. Some of the meanings you might naively think of are actually wrong. Right? And so you need to define it so that it's true. Right? And that's something that surprisingly got rather neglected over a long period of time after the invention of quantum mechanics. I think partly because nobody was doing any experiments where you had a many-body system which was truly quantum mechanical, which was isolated from the environment. So it was just a angels on the pin type question. So people didn't really focus on it. And it was actually the people doing first classical chaos and then going to quantum chaos who were the first ones to really make some real nice statements about this. But then more recently, it was more driven by, that was driven by classical, people were doing experiments on classical chaos, and then people said, oh, what happens when we go to quantum mechanics? And people did do some experiments on quantum chaos later on, but only after the theoretical. But then people now, of course, as I said, are actually building these kinds of systems and doing experiments on them with cold atoms or trapped ions or whatever. And so these questions are much more germane today. And in some sense, I would say Anderson in 1958, the paper I mentioned, was the first one to really begin to say something non-trivial on this subject. Okay. So this does not mean rho of t goes to some sort of equilibrium probability operator. And you can actually see that from here. And here. So here you have some initial condition. And you go to late times and you get this, whatever it is at that time. It's time evolving. And at any of these times, we can always just run the dynamics backwards and get back the initial one. So it does not mean this. Right? So all info about the initial condition, rho of 0, remains in the system. So the full system, does not go to equilibrium or even forget anything about the initial conditions. It remembers everything about the initial conditions because in principle you can just run the dynamics backwards and get the initial conditions. It's all there.
Can I ask a question?
Yeah.
But why does that mean that it won't go to a constant?
A constant independent of the initial state. So that's the assumption here.
Oh.
When you say a system goes to thermal equilibrium, it goes to a constant independent of the initial state.
but it can still go to a constant. No, but I mean.
Well, it doesn't go to a constant. And it doesn't go to something that's independent of the initial state, even if it's dynamic. Right? This always has dynamics. It's always changing. And it's different for each possible initial state. So the full system in a strict sense doesn't go to equilibrium in this sense here. That t goes to infinity, it goes to some equilibrium.
Sorry, but how do you know for a fact that rho will never at some point commute to Hamiltonian and clear the
Well, if rho commutes with the Hamiltonian at time t, then it commutes with the Hamiltonian at all times, just by time evolving it. And so it had to. So that's a very special initial condition. So yes, there are initial conditions for which rho is time independent, and those are initial conditions. They're called the eigenstates of the Hamiltonian. And we're going to return to them. They're very important initial conditions to think about. Right? Was that your point, Mike? Thank you. Yeah.
So, but isn't the dynamics of the system, if it's finite, isn't it quasi-periodic in some sense?
Yeah.
This issue?
Yeah, with n squared periods, yes. Yeah.
So this definition of t going to infinity, is it really?
Well, this is not true, so
Right.
so we don't really need to define it very well.
I'm referring to the statement that you put on the top, that you're talking about something of t1 to t.
Yeah, right. We're trying to define this, but I haven't defined it yet. Right? I'm just saying the obvious definition is not what we want because it's not true. That's all I'm saying so far. Okay. But I want to say a little bit about it, right? So all of the information remains in the system. And where is it? It's in these operators here. Right? When you expand the state of the system in terms of all these operators, the information about the initial state gets hidden in these very high order spin-spin correlations that are just impossible to measure. Right? So as a practical matter, the information is gone as far as experiment is concerned.
This statement is about the full system.
Yeah, right. I'm still talking about just the full system. Yeah.
So if I look at the local system, it may equilibrate and
Right. So what we got to do now, sorry, yeah, you're stealing my thunder. Right. Right. And as I said earlier, that's what dissipation and that's what decoherence, dephasing is about. It's not about loss of information. It's about information getting hidden, and the place it gets hidden is in these typical highly entangled, you might say, or operators that involve many, many degrees of freedom and are just, as a practical matter, inaccessible. But in quantum mechanics, the information doesn't go away, it just gets hidden. And that's what decoherence is. It's hiding the information.
Excuse me.
Yeah.
Why do you stress in quantum mechanics? This is also true in classical mechanics, right?
No.
I can reverse the dynamics also in classical mechanics, and they go back to the original condition, right? Nothing is lost.
Well, yeah. So this is not true in classical mechanics. So yeah. Let's after I say what I want to say about quantum mechanics, let's return to classical mechanics. It is pretty much the same. Of course, classical mechanics is just quantum mechanics on large scales, right? But classical mechanics has one difference, which is it's more true for quantum systems than for classical systems. So quantum systems go to equilibrium in a stronger sense than classical systems because of fundamentally their initial state has some uncertainty. Whereas a classical system doesn't have to have any uncertainty in its initial state, and so therefore will have no uncertainty in its final state, and time evolution is deterministic. Whereas quantum mechanics, you can't really do that. Right? You can do that in this sense here, in terms of the probability operator, but you can't do it in another sense, which I'm just going to get to right now. Yeah, but if I don't get back to that, either later today or tomorrow, bring it up again. Okay, so as was said, what thermalizes are subsystems. Of the full system. And what happens is the remainder, so if we have, so let me just draw over here. Here's my full system, and so that's this box here. I've drawn it as an ellipse instead of a box. It's still isolated. And instead of looking at the full system, let's just look at a subsystem. Not necessarily a subsystem in real space. It could be a few, if say it was a particle, say we had some particle, let's say we had periodic boundary conditions, and this could be the certain momentum states. It doesn't have to be in real space. It could be some degrees of freedom, not necessarily real space. And I'll call the remainder of the system B, because it's going to act as a bath. So we have our subsystem here. Subsystem. This encloses the full system. And what happens when the system thermalizes, of course, right. So not only I'm trying to make a definition for this statement, which is true for systems that do go to equilibrium. Another part of my lectures will be not all systems go to equilibrium. Systems that are localized don't go to equilibrium. Right? And so even when I get the right definition, it's only going to be true for some systems. But I want it to be true for at least a broad class of systems. And so in the systems that do go to thermal equilibrium, what happens is the subsystems thermalize, and the remainder of the system which I've denoted by B there. B is this all the other degrees of freedom that are not in the subsystem, serves as the reservoir to equilibrate S.
I'm sorry. So did you define what thermalization means?
Not yet.
Okay.
Yeah, that'll come. It means go to equilibrium, go to thermal equilibrium. Just like it does it really means just like what you learned in statistical mechanics, but I need to, define it a little more carefully than you usually do, right? And so I'm not ready to do that yet. And this is true when the subsystem, this works. This is what happens if the subsystem is much smaller than the full system. Say measured in entropy, for example. And the statement that the system goes to thermal equilibrium as a precise statement is only true in the thermodynamic limit. Finite-sized systems don't exactly go to thermal equilibrium. And so I'm going to be taking the thermodynamic limit on my system to make these things sharp statements. Mike?
Can you clarify what you mean by one being smaller than the other in entropy?
Right, and when it goes to its, at late times, the entropy of the subsystem is small compared to the entropy of the full system.
The full system's in a pure state.
Okay, then it is small compared to the sum of the entropies of subsystems over all the bath. Yeah. Yes, ma'am?
Will your definition depend on how you partitioned S&B, like whether it's field space or momentum space?
I need to make one proviso. So there will be a restriction on how I divide the system, which I'm going to get to. Okay. Right, okay, so this is what happens for systems that thermalize. And as I said, not all systems thermalize, right? Some systems thermalize, some systems are localized and they don't thermalize, right? And so let's talk now only about the systems that thermalize, and the sharp distinction between whether you thermalize or not, it's really only a sharp distinction. It's like a phase transition. It's only like it's only a truly sharp distinction when you take the thermodynamic limit on the full system. The subsystem can remain finite, but the full system taken to infinity, right? In order to make this a sharp distinction, it's like a phase transition, and that's the phase transition between thermalization and localization. Okay, so actually let me just write that here because that's my next thing, is to try to set up to do that a little more carefully. So sharp distinction between thermalization and not requires n to infinity. Take a large system, because it's basically a phase transition. Okay, and so as we take this limit, we're going to have a family, of course, we're going to have a family of Hamiltonians, making our system bigger and bigger with more and more degrees of freedom, and so we have to have a family of Hamiltonians, and we have a family of initial states. So we need such sequences. Okay, so now I'm going to start getting to Yasmin's question a little bit. Okay, so we got to talk about, or I want to talk a little bit about conservation laws. So our Hamiltonian so we're going to have conserved densities, which are extensive conserved quantities. So that's extensive operators that commute with the Hamiltonian law, right? And extensive meaning they're proportional to the size of the system as they take the thermodynamic limit. Okay. So one of them is H, the energy, except in Cloquet systems, where you don't even have that. Okay. And then we could have things like particle number. So we might have various kinds of particles in the system that are conserved, or we might have spin, some total spin, or maybe just one of the components of total spin, or possibly other conserved quantities. If my system is an integrable system, I have an infinite sequence of such conserved densities, which are the integrals of motion of the conserved system. And I actually want to present this including them as conserved quantities. Okay. And when the system goes to equilibrium, the bath is serving as a reservoir for the system, and any conserved quantity is being exchanged between the reservoir and the system. Right? So the subsystem has to be able to exchange all the conserved quantities with the rest of the system. And so that's the restriction, right? So we could have a conserved quantity, and then we could choose some set of degrees of freedom where this is somehow in momentum space or something, or this is the number of particles, right? So we could have the conserved quantity so it's purely in the subsystem or purely in the bath, and there's no, well, particularly the problem is if it's purely in the subsystem. And so we need to partition it if you partition it in a way such that the extensive conserved quantities that need to equilibrate are all in the subsystem, then you're not gonna thermalize, because you won't really exchange that with the reservoir, and you will remember the details of the initial condition on that distribution of that conserved quantity, because it's all in the subsystem and it never leaves. Right? And so there is a restriction. Basically that. I think that's the only one I'm aware of.
So
Leo?
so you're saying with that proviso, you, even integrable system will thermalize?
Yeah, I'm going to try to do the definitions so that integrable systems are in the same framework as systems that thermalize. It's just they have an infinite number of conserved densities rather than a finite number. But I'm trying to, this.
So you could get on
If you guys figure out a reason that this is a flawed way to present it, please tell me, because I've never actually done it this way before in public. But I think it works.
So you could get unlucky. You have a system and you pick some S to be in some pocket where this provides this requirement doesn't work.
Yeah.
And then it will not thermalize. But when you pick another region, that region will thermalize.
Yeah. Although, you don't necessarily want to call these regions, right? This is a set of degrees of freedom. They might be global degrees of freedom. So there's no implication that this is real space, this picture. There's some set of degrees of freedom here in a Hilbert space here, and there's another set of degrees of freedom out in the bath in a Hilbert space there, and the full Hilbert space is a product of those two Hilbert spaces. That's really the only structure we're assuming. But if you have, if one of these conserved densities is an operator that is the identity on the bath and only acts on the subsystem, then the bath isn't serving as a reservoir for that quantity and you won't thermalize.
Right, so that's like, it'll be like microcanonical with respect to that.
Well, then I have to look inside of here and take subsystems inside of here and ask if they do equilibrate it. So you just, right. Now, I'm doing microcanonical on this scale, right? You're saying, yeah, you're absolutely right. Under that circumstance, I could then do microcanonical on this scale. But this subsystem, for what I'm doing now, this subsystem could be just 1 or 2 degrees of freedom. Right? I'm not going to take the thermodynamic limit on this guy, and it could be just 1 or 2 degrees of freedom.
No, I meant microcanonical with respect to that conserved density. In other words, S can still be described by.
No, but let's say the initial. Okay, right. So our initial conditions, right? Okay. Let me. There's another proviso on the initial conditions. Initial conditions in limit n goes to infinity have 0 uncertainty in conserved densities. Over the full system, right? But they're allowed to have uncertainty in the conserved density as long as it's subextensive. And if I put a subextensive uncertainty inside of a finite system, it'll never go away. So in that sense, it'll have a memory of the details of the distribution of that conserved quantity that I put in my subsystem. Right? And I don't want that. Right? I want to equilibrate all systems. So the only restriction is 0 uncertainty in the density. So you're allowed to have uncertainties in the conserved quantities just as long as they don't diverge. They have to diverge. If they can diverge, and typically they will diverge, typically a square root of n. But they can diverge as fast as any power less than 1 of n. And then the density will be well defined. Right? And that's what we want. So that's a proviso on the initial conditions. So conserved densities are each assumed to go to a limit and goes to infinity.
David, this is a huge topic for discussion in these definitions. Are you assuming that these conserved quantities are local in the sense that you defined on the left board?
Well, in the integrable systems, I can't assume that because there's an infinite sequence of them which go to arbitrarily high order. But yeah, for the non-integrable systems, yes. But let's allow also integrable systems where we have an infinite sequence that go to the limit of arbitrarily high k. Yeah?
So your definition involves some choice of subsystem. Is it supposed to work for any subsystem of some certain size? Or
Yeah, the idea is any subsystem, any subsystem, as long as I take the thermodynamic limit on the bath, not on the subsystem. So and any initial state satisfying just this, I think just this restriction.
Within this constraint, if it is doesn't thermalize, will it always go to localized phase? Or let's say it doesn't thermalize for some reason.
Well, as far as I know,
It will always.
the only case we know of that doesn't thermalize is localized. Now there's the critical point between thermalization and localization, which probably we don't know whether it thermalizes or not. So there may be another case there. Maybe not. My suspicion is the critical point, well that's delicate and not understood. Right? But, okay, so what I'm telling, so the stories I'm telling you, none of this is rigorous, right? And there's a lot of open questions. But a bunch of the stuff I'm talking about has been tested as well as you can numerically, which isn't very well, and I'll tell you about that. But it's a story that holds together against thought and against numerical tests. And a big challenge is to, increase that support for this whole picture, or maybe undermine it, because it is a rather heuristic picture at this stage. Although we're trying to make things at least well-defined, if not proven, at least well-defined, right? And the definitions, there's a lot of debate about what definitions should you use. And there's a lot of different definitions, and I'm sort of giving you my favorites today, right? And I reserve the right to change my mind about that, right? So that's sort of the situation here. This is, stuff that, in terms of really diving into it and thinking about it really carefully, it's very recent. And it was a very small community of us until this year. And I'm hoping the new blood in the field will actually make us go further, because there's a lot of pretty smart people who have started thinking about this problem in the past year or so. And I'm optimistic of more progress. But I'm recording where we are right now in what is admittedly very likely an incomplete story. Okay, so we're going to consider this subsystem. We're going to take the bath, the full system in the bath will go to the thermodynamic limit. The subsystem will stay finite and even perhaps just 1 degree of freedom. All conserved quantities, all extensive conserved quantities are shared and moved between S and B. We not only need that the conserved quantities are both in S and B, but also that the Hamiltonian moves them between S and B. Right? So you need a restriction on the Hamiltonian. It actually has couplings between the subsystem and the bath, right? Although that's typically the case. And that division need not be in real space. Okay. So now, what do we mean by, okay, so we can talk about the probability on the subsystem, rho sub s of t. So the probability operator for the subsystem. Now this is usually called the reduced density matrix, aka reduced density matrix. Although the reduced is kind of redundant because as far as I can tell, all density matrices are reduced because you've traced, you're ignoring the rest of the universe. So I think all probability operators are reduced density matrices. But when someone's talking about a full system and ignoring the rest of the universe, and then they talk about a subsystem, they call it a reduced density matrix rather than the density matrix of the full system. But when you talk about the full system, you're ignoring the rest of the universe, and so it's already a reduced density matrix.
Well, but if it's not entangled with it,
then it's still a reduced density matrix. But it is entangled with it, right? What I'm saying, it's always entangled with it. There's no experiment that can take a many-body system and prepare it in a state that's not entangled with something outside. It's not going to happen.
In quantum
It's too hard.
computing, they're supposed to be doing that.
Excuse me?
In quantum computing, they're supposed to be doing that.
No, they just live with it. Because as long as it's just entanglement and there's no interaction, it's harmless. You can live with it, right? And that's a big thing in quantum computing, is living with the imperfections, right? Working with it. Yeah, that's an idealization they want in quantum computing, but they don't have it. And they know they don't have it, so they have to figure out how to live with the entanglement with the rest of the universe that's there in the initial state, right? And that gives you less than 100% fidelity and all this kind of stuff, right? And that's the reality, and it's never going to change, right? Maybe it'll get closer to 100%, but it's never going to be perfect. Okay, and so what is this? The probability on S is just a trace over all the degrees of freedom in the rest of the system of the probability operator of the full system. And let me just put an N on that. So so this is the full system. And we're going to take N to infinity. So I'm just going to put the N there just to remind us that we want to do that. Okay. And of course, I erase the dynamics of this. So this guy is just undergoing unitary time evolution. But after a trace, this guy's evolution is not unitary. The trace operation doesn't preserve unitarity of the time evolution. And so what thermalization is, so now I'm going to try to be precise. Thermalization means limit, okay, so limit goes to infinity, limit n goes to infinity, rho s t equals rho s equilibrium. And this will have some parameters. So for each conserved density, so we have a list of conserved densities. And for each one, we have a Lagrange multiplier. For the energy, we have the temperature. For the particle numbers, each particle number, we have a chemical potential. For the total spin, we have some effective field, right? And we do thermodynamics. You know, when you learn statistical mechanics, and probably all of you, you start talking about the microcanonical ensemble, which is sort of conceptually the cleanest, but very hard to work with. And what you do, then you say, oh, I'm going to look at a subsystem, and you find the subsystem is in the canonical ensemble, say if it's exchanging energy with the rest of the system. That's just what I'm doing right now, right? And so this subsystem should be in the distribution that corresponds to the ensemble associated with all these particles, which are being, all these conserved quantities, which are being exchanged with a bath, right? And so if there's only energy being exchanged, I will just have a temperature, right? And this is the temperature that this energy density corresponds to in the thermodynamic limit if it went to equilibrium, right? If I have particle numbers for each, I will have a chemical potential, right, etc. So equilibrium is specified by the various conditions, the Lagrange multipliers that tell you about exchanging the conserved quantity with the bath. Standard statistical mechanics. Okay, and you're going to have one of these for each conserved quantities. For an integrable system, you're going to have an infinite sequence of such coefficients which correspond to the infinite number of conservation laws. These are set by the initial conditions. Each one of these, right, the initial condition has a definite value of the conserved quantity, and that sets these, each one of these coefficients. So it does, the system, when it goes to equilibrium, it does remember the subsystem, knows some things about the initial condition, and what it knows about the initial condition is it knows about all the conserved densities in the initial condition.
For the entire system.
For the entire system. If the subsystem is very small, it probably doesn't have a big enough Hilbert space to probe information about an enormous number of operators. So if you had an integrable system, and I only looked at a very small subsystem, I wouldn't get all the information about all the conserved quantities. In order to do that, I have to do a pretty big, the bigger the subsystem, the more information I learn about. But if it's just energy, all it takes is one spin, for example. Say there's a field on this spin. If there's a field, if this is one spin and there's an effective field on it, by measuring its magnetization, I know what its effective field is. I know what its temperature is, excuse me. And so if there's only conserved energy, I only need 1 degree of freedom to learn about the temperature.
Somehow you're defining thermalization by...
The equation's not done. This is an equation. I haven't defined this. So I said thermalization is if this becomes this, but then what does this mean? Right? I haven't defined this. I'm sort of telling you what the symbols mean here. Right? And so now I'm going to define this.
Suppose you were a microcanonical ensemble, so you didn't have a definition. You only had a definite energy. You didn't cut out. You really were dealing with that. You didn't separate the system with that.
Leo, let me finish this here. And finish, because I think I'm going to address your question. Let me try. Okay, so what is this? So what this is a trace over the bath of the equilibrium of the, I guess it'd be limit, n goes to infinity, trace over the bath, equilibrium at those temperatures, all those things, right. Right. And so here, this guy, as I've defined it, it only depends on, right? And then equilibrium, there's just a map. Energy is a function of temperature, which is invertible. The temperature is a function of energy, right? So the full system is microcanonical. It has a definite value of all the densities. That corresponds thermodynamically to a definite value of all the temperature, the chemical potential, and all those things. This is just from thermodynamics. Okay? And so we take the full system, pretend it's coupled to a reservoir, calculate this, right, which is, this thing here is e to the minus beta h minus mu I n I, sum on I, plus dot, 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 right? So this is equal to that. So this equilibrium is just a Boltzmann-Gibbs type equilibrium. We put that in here, take the trace, and then that gives you the probability on the subsystem at equilibrium. No assumptions made about the strength or the weakness of the interactions between the subsystem and the system. So that's why I'm doing this way. Traditionally, this is done just write the Hamiltonian of the subsystem. But that's not right, because the subsystem is strongly interacting with the rest of the system. And we can't ignore those interactions. And so you have to take the Hamiltonian of the full system, go to equilibrium, trace over the bath, and that gives you the equilibrium for the subsystem. So this is thermalization, I think. I think this is a good definition of thermalization. Let's put it that way. Yeah.
So what we can
usually give for the larger system are the conserved quantities. And then how do we find out T and mu? How do we find out the way to find these Lagrange multipliers? Do we take the trace of rho and equilibrium and then somehow fit it to e to the power minus beta h?
Well, you need E of t is just 1 over z. You know what z is? Trace e to the minus beta.
Well, I don't
Blah, blah,
really know
blah.
what z is, right?
Hmm?
What I'm given is some initial mixed state. Do I take the
No, you have a
initial mixed state?
Hamiltonian.
But do I take my initial mixed state to be of the form e to the power minus
No,
beta
no, no.
h?
No, the initial mixed state is anything you want.
Right.
But I'm going to ask you to tell me what are the values of the conserved densities in that initial state. That's all I'm going to ask you. Be far out of equilibrium. In fact, I'm interested in the case where the initial mixed state is way out of equilibrium. But I'm just going to ask, what are the conserved densities? Right? And if I know the conserved densities, and I know the Hamiltonian of the system, in principle, I can get these parameters here.
So you can make up a Boltzmann-Gibbs distribution to give me those average quantities as the conserved quantities as the average densities.
That's right.
And then and you're saying that thermalization will involve exactly those parameters.
Yes.
To this.
Yes. Because basically what's happening is the rest of the system is acting as a bed. Right? And so this subsystem is in contact with a bed. And so it's the standard situation for calculating Boltzmann-Gibbs statistics. Right? But there's just a few steps that I'm saying, that you really should do right in order for this to be true. And I just wanted to show them. I want a definition which works even if the interactions between the system and Beth are very strong. And I want to ask, what are the restrictions on what the Hamiltonian could be and what the subsystem is and things like that. And I think I've outlined the important provisos. There may still be some more. Alex.
One statement you're making is that you go to a stationary limit, right? So you do
for the subsystem.
Now I guess it's relatively easy to come up with examples that are not too exotic, where the classical system would go stationary subsystem, but the quantum system will not. Austin Lamarcraft is
taking into account all conserved quantities?
I think it would pass all the tests here.
Yeah.
Example. Taking angular momentum from a big stick.
Yeah.
And let's assume that it has a chaotic dynamics. It's not necessary, but that's the same. And that's our small system. And now it talks to the rest of the universe, but in a manner that will not will conserve the total angular momentum of the subsystem. Some weak or coupling to some other one. Now, our reduced probability, how is the probability matrix? Is a finite dimensional matrix. The size of the spin sets the dimension of the matrix. And in particular, I can look at its matrix elements in the coherent state basis.
But you're saying now the subsystem has some conserved quantity.
No.